So I hope you all can see my screen and can hear me as well.
Yes, ma'am.
Yeah. Okay. Fine. So today actually we were going to talk about gauge origin invariance in particular, which is part of the general concept of gauge transformations and gauge invariance of physical properties. But before we start on that, I will just do a little bit of recap of the Hamiltonian, which we did last time, and then I will continue. So today we will talk about the gauge problem. Okay. So let's see. Okay. So last time we said that the Hamiltonian is basically the classical quantity which enables us to go from classical to quantum mechanics. And it is the Hamiltonian which features in the Schrodinger equation. So it is important for us to formulate this Hamiltonian for the problem of interest. And the Hamiltonian is basically a function of the position of various particles. So I is I of the ith particle, let's say, and pi is the momentum of the ith particle. So the Hamiltonian basically is a function of the position and momentum, and when you evaluate it, you get the energy of the system classically. Okay, and you have some equations which called the Hamilton equations, which related to the forces on the particle and basically the Newton's laws which the system is obeying. So Qi dot is del H del Pi, and Pi dot is minus del H del Qi. So these are what are called Hamilton's equations. Okay. Now, since you see that the forces on the particles, which are the real quantities, they're related to the derivatives of the Hamiltonian, uh, you can always add a constant to the Hamiltonian. So the Hamiltonian is not unique. In that sense, okay, but uh, but given a lot of conventions, according to the system you're treating, you will have more or less a unique Hamiltonian for the for before you start solving the Schrodinger equation, because they're already decided by classical mechanics, the freedom that is there in the Hamiltonian. Okay, so very simple Hamiltonian, which is basically what we will base our Hamiltonian on, is that of a particle in a scalar potential. So that will have a kinetic energy, which is p square by 2m, and it will be subject to some sort of external scalar potential, Vq. Okay, and if you do del V del Q or minus del V del Q, then you get the force on the particle at position Q. So V is also a function of position Q. Now we can verify its equivalence to Newton's equations, which we also did last time. So how do we do it? We use Hamilton's equations, and then Q dot is del H del P, so 2P by 2M. Okay, and V is not a function of P. So there, so you have P by M, and P dot is equal to minus del H by del Q. That is equal to minus del V by del Q, which by definition is Fq. Okay, and from here, if I take another derivative, okay, then I have Q double dot equal to so is equal to P dot by M, and P dot is FQ. So what you get from here is basically that MQ double dot is equal to P dot. So you can already see this is Newton's second law of motion, that mass into acceleration is the rate of change of momentum. But we can go a step further, and P dot is basically FQ. So force is equal to MA. That is Newton's equation. Second law. This is it. And then what is the recipe for going from classical to quantum mechanics? If I want to go from classical to quantum mechanics, the two replacements that we do is P goes to minus IH cross del, which is the momentum operator. Okay, position stays as position, and the Hamiltonian, if you wanted to transform that directly, that is IH cross del del T. So this is what features in the time dependent Schrodinger equation, which is H psi equal to IH cross del del T of psi. So now, when so these Hamilton's equations, when the fact that they give you the Newton's laws, this is only true for conservative fields. So if you remember, the Newton's laws are also actually valid only for conservative fields. So in case of
Hello, ma'am.
yeah,
I just have one question. Like here, when we are doing this thing, like this one is true in only position representation, right?
yes, this is true only in position representation.
Okay. Should we have to like every time specify that, or is that okay? Like in our project, especially in our things, are we changing anywhere? Is it required or?
So actually, more or less everything is done in the position representation.
Oh,
I have only used the momentum representation when we were being taught in class, and I've never come across it in a paper or done it myself ever again.
okay, okay, ma'am.
So I think it is fine to just stick to the position.
Yeah, I just wanted to ask because I just want to clarify. Thank you.
Yeah, I think it is the position only that is carried. If we ever need momentum, then we'll think about it. Actually, I've even forgotten most of the momentum representation things, I think. Okay.
Thank
Yeah.
you, ma'am. You can
Yeah,
continue.
no problem. So I'll continue. So the thing is that so because this is applicable for uh, conservative fields, then that means that your system cannot lose or gain energy in the field. So then, as soon as you think about magnetic fields, which is what we are interested in, magnetic forces are dependent on the velocity, so they're not entirely conservative. So they're not conservative. So then you have to start thinking in terms of time dependent electric fields being produced by magnetic fields, or vice versa. So you have to start thinking about how the electric and magnetic fields change depending on each other's time dependence. So then we have to go over to Maxwell's equation. So Newton's laws are entirely they deal only with particles, more or less. So the fields are only appear in the equation as forces. Okay, and these forces are position dependent, and in most cases, if you have a velocity dependent force such as a magnetic force, then Newton's laws become very difficult to use, because there are because then the forces change with the velocity of the particle, and the forces also then depend on the acceleration of the particle. And if you really think of the details, it is possible to write out Newton's equations for every all these things together, but it is much more cumbersome. Instead, what one shifts to is the Maxwell's equations. Okay, so I'll just write down the Maxwell's equations. So there are 4 of them, as you know. So there are 2 which tell you about the source of the fields. These 2. Okay. And there are 2 others which tell you about the relations of the fields, magnetic and electric fields, with each other. Okay. So these are called the homogeneous pair of Maxwell's equations. So they only involve the electric and magnetic fields. And what it tells you is that if you have a changing magnetic field, you will generate an electric field. That's equation 4. And when you solve 3 and 4 together, you get a description of light as electromagnetic radiation. So this you must have already heard of, at least, if not studied in great detail. And then 1 and 2. So 1 and 2 tells you how the fields are produced. So the equation 1 tells you that the electric field is produced from the charge density in a given area, right? And the second one tells you that the magnetic field can be produced from a changing electric field as well as from J. J is the current density. So current density basically means the electric flux in a region. So if you have flowing charges, basically, you can quantify that in terms of flux, and that gives rise to a current density. And rho is called charge density, which is a static thing. It tells you the distribution of charges in area. So these are the 2 things. And then when we look at these equations, we can make some conclusions about what form my electric and magnetic field should have, okay, in terms of the potential. So if I say that my electric field is produced by a scalar potential phi and my magnetic field B is produced by a vector potential A, then how they are related to each other is determined by 3 and 4. So phi is a scalar potential and A is a vector potential. Okay. Then let me just check if it's still recording. Fine. So from here, let's see. So equation 3 directly tells me that the divergence of B is 0. So we can just leave it as such. Okay. And then if I solve for B from it, that is by integrating. So the divergence operator is the derivative operator. And if I integrate it, then it will tell me that B will have a form which is the curl of some quantity. If you do that, then you satisfy the equation 3, because the divergence of a curl is 0 by construction. So if I choose fields such that they are curls of some function, here A, we don't know what form A is. Okay, this is, let's say, an arbitrary function. Okay, so it's an arbitrary function, and we are identifying it as a potential because the field is the derivative of that function. Okay, so A is not something we have constructed first. So it's the field that we know, and we know that the divergence of the field must be 0. So we say that, okay, then since we know that the divergence of a curl is 0, I can take B to be the curl of a function. Okay? And since the curl is also a derivative operator, we can call this function a potential. It must be a vector potential by construction. Okay, so this is just, so A has no physical significance as of now. It's just mathematical in order to satisfy 3. Okay, and then if we use this 3, if we use this equation, the fact that B is the curl of A in Maxwell's equation 4, okay, if we do that, then what do we get? Then we get so let's number this to 5. Put 5 in 4, and then I have curl of what did I do? Did I do something? Curl of E plus del T of curl of A is equal to 0, which means now, so I'm taking the curl common, E plus del A del T is equal to 0. This tells me that E plus del A del T is equal to minus grad phi. So again, this is a mathematical solution in the sense that if the curl of something is 0, then that something can be written as the gradient of a scalar function. So this is a, okay, let's say arbitrary vector function, and this is an arbitrary scalar function. This we conclude from mathematics, and again we identify it as a scalar potential because E is a field. Okay? And the minus is a convention. The minus is not doesn't come from mathematics. So then, what are my solutions to equations? So solutions to 3 and 4 together is that E is equal to minus grad of phi minus del A del T, and B is equal to curl of A. Okay. Then, but we still don't know what phi and A are. We just know that one is a scalar potential, one is a vector potential. What they should be for a given E and B are actually determined by equations, Maxwell's equations 1 and 2. But the problem there is that is determined by 1 and 2 because 1 and 2 actually tell you what the value of E and B is. And once you know the value of E and B, you can find out the value of phi and A. But the issue here is that this rho and j, they are also changing. So they are changing according to E and B. So if E and B are external fields applied on a system with charged particles, then according to the field, these particles will move about. Okay, and you will have a charge density generated and a current density generated. So, and if you change E and B, rho and J will change. So since rho is dependent on E and B and J is dependent on E and B, then you cannot directly solve 1 and 2. Okay. Now, if you were only concerned with a system where you have moving charges which are moving on their own, not due to a field, okay, they're moving because of some other reason, and you want to calculate the fields that are generated. Okay, in that case, it is possible to solve equation 1 and 2, and you will obtain the field generated by these moving charges. So that is actually the problem that Maxwell's equation was addressing. But when, for us, if you have a molecule or an atom with moving electrons placed in a external electric and magnetic field, then it becomes a more complicated problem, because these moving particles will now adapt to the externally applied fields. So in our case, actually, the fields have to be, so the fields that I apply are known, but to this you add the fields that are generated by the particles, and you get a net field, and these net fields will satisfy equation 1 and 2. So this is a more complicated problem. But anyhow, that is not the problem we are solving, so it's okay. So for us, the problem stops at finding out rho and j, let's say. So if I find out the wave function of my system in an external electric and magnetic field, then from that wave function, I can find out the charge density rho and the current density j. Okay, and that is where we stop. If we wanted to now find out the fields generated by these particles as well, then we would require 1 and 2, and then it's a complicated problem. Okay, so you get my point. So we are not going to solve 1 and 2. So for us, actually, 3 and 4 are good enough, which tells me how the electric and magnetic fields are related and what form they should have. So that's all. So for us, looking at the Maxwell's equations, we have only two important things: this and this, and that too. If we take static fields, then the change of, and this also in most cases will be 0 for us. So just the fact that E equal to minus grad phi and B equal to curl of A, just this much conclusion from Maxwell's equations is good enough for us. Fine. Now we come to the gauge problem. So what is the gauge problem? The gauge problem is that since the electric and magnetic fields are defined by derivatives of potentials, then phi and A are not unique. So there is some freedom in the choice of phi and A, which give the same electric and magnetic fields. Okay. So now if it was only electric field, then it is obvious that if I do phi prime equal to phi plus some constant, any constant, it will still give me the same electric field. Okay. But here, since E and B are coupled, it is not exactly just a constant, the solution is that if phi prime is phi minus the time derivative of some arbitrary function, and correspondingly the vector potential is shifted by the gradient of the same arbitrary function, where f is a function of position and time, okay, then E prime equal to E and B prime equal to B. So this is, so if you put back this phi prime and A prime in Maxwell's equations 3 and 4, you will be able to see that if you simultaneously shift A with the gradient of a function and the scalar potential with the time derivative of the same function, then you get back the same E and B. Okay. And since we are concerned most with B, then let's look at B prime actually. So B prime is the curl of A prime. So it is the curl of A plus grad f. This is B plus curl of a gradient, and we know that this is 0. So B prime is equal to B. That's simple. Okay. Now, how will we choose f? If we are, so the gradient of a function is a vector, right? And if the function is arbitrary, you can basically generate any vector. So that makes your vector potential really, really arbitrary. So we need to impose some additional conditions from physics preferably, and then decide or at least restrict the domain of f. Okay. So let me mark. So the fact that you can add this to A is called gauge freedom, and then we will make a gauge choice based on some physical considerations. So in case of atomic and molecular systems, I've mentioned before that the additional condition that is chosen is that the divergence of A is 0. This is called the Coulomb gauge. Now if you ask me why the choice is this, so one hint is that so the divergence of B is 0. So if the divergence of A was also 0, that just, well, it looks good, but that cannot justify choosing this condition. It could have been something else. But what has been seen is that when you use this Coulomb gauge in various problems, such as the Schrodinger equation, or I don't know, interaction of, not sure, let's see. Well, basically for things where you're dealing with atomic and molecular systems, where you have localized charges, then it simplifies the equations that you handle. So that is, I would have loved to give you a very physical understanding of why the Coulomb gauge is useful for atomic and molecular systems, but I am not sure, or it's not clear to me exactly if there is a physical rationalization at all. Okay, so the thing is that if you have a divergence of A equal to 0, it simplifies a lot of things, because you get second derivatives of A in many equations, and if one derivative is 0, you sort of simplify things. So we'll see how it simplifies things when we solve our problem. But if there is an actual physical logic to it, I am not sure. Okay. So maybe you all can also think about it if it makes, if you can rationalize it. But it's like for atomic molecular systems, Coulomb gauge is used when you're when you introduce like time dependent fields. Then you have the Lorentz gauge, which is used. Then there are other things. I have come across the names like Weil gauge and some other names as well for other problems. Okay, and they're always somehow related to simplifying equations. Okay, so I'll also think about it if I can give you a better reason. But for now, just accept that we use the Coulomb gauge and the condition, and this is the additional condition. Okay, but this does not uniquely specify the function f either. Okay, so it restricts the domain of f. How does it do that? Because if you impose the Coulomb gauge, okay, then that that means that divergence of a prime is also zero. Divergence of a plus grad f is equal to 0, and divergence of a plus divergence of f is equal to 0. And you want both a and a prime, both of them, both their divergences to be equal to 0. So this is also equal to 0. And that gives you that the second derivative of the function is 0. And this is a simple differential equation, so you can solve it for a class of functions for f. Which is basically that so this is, oh yeah, I remember, I forgot the name. So this looks like a special case of like Poisson's equation. Do you remember? This is a very famous differential equation. So you have a set of solutions for the function f. So it gives you a class of functions, imposing the fact that the divergence of a is 0. Okay. But there is still some freedom in this because, like I said, it's a class of functions. It's not a unique function. So let's continue now a little bit more. So do you remember the Hamiltonian that we spoke about? So let's go back to our problem, which is basically that you have some charged particles moving in a magnetic field. So the Hamiltonian, if you remember, I defined something called pi, which I called the physical momentum of the particles, which gives you the kinetic energy, and you have a scalar potential phi. And what was the definition of this physical momentum? Was that it was P plus EA, where P is the canonical momentum. So this is the physical momentum, and this is the canonical momentum. And the canonical momentum is what is replaced by minus IH cross del, and then you have plus A. Okay. Now, from here, if we expand this pi square, so h psi is what we need to evaluate, right? So this is what we need to evaluate. So let's first see what pi square psi is, which is the most difficult one, because E phi is just multiplicative. So what is this? So this is P plus EA into P plus EA acting on psi. That is equal to P square psi plus E A dot P plus E P dot A plus E square A square. Oh, sorry, forgot the psi. Psi. Okay. Now dot products are commutative, so A dot P is the same as P dot A if A and P are just vectors. But remember here, P is a derivative operator and there is a function or two functions. So if you have P acting on A phi, then P can do a derivative of A and P can do a derivative of psi. Okay. On the other hand, if you have A dot P, then P can only take derivative of psi and A is just multiplicative. So you have to be careful. It's not, you cannot just say A dot P equal to P dot A. That is the difference between operating or deriving things with operators and deriving things with vectors. So this is this, and then you have P squared psi. Okay. And so this one is just E A dot P psi. But here we apply the product rule of derivatives and we get E is, you have something where P acts only on A and psi is multiplied, and you have another term where P acts on psi and A is multiplied. And this is just a multiplicative thing. So you have P squared psi, and so this and this are the same. So I can have 2E A dot P psi, you have E P dot A psi plus E square A square psi. Okay. Now so okay, now we will see the usefulness of the Coulomb gauge. So in P dot A, so what is P dot A? I'll just write it. I don't feel like copying again, so I'll just write over here. This is E, you have minus IH cross divergence of A psi, and this is 0. Okay. So I reduce one term here, and I am left with 3 terms: P square psi, 2E A dot P psi, and E square A square psi. So I have 3 terms now. I got rid of one by using the
No,
Coulomb
ma'am.
gauge condition. Yeah.
Can you explain this thing like how did you get this factor of 2? Can you explain?
Oh, okay. I got it from this one.
Yeah.
So this and this. Sorry. So the ones I ticked. This one and this one. They're the same term. So A dot P psi is the same as A dot P psi because A is A is just a vector at a point for every point. So I can, so A dot product is, what is it called? Associative. So these two terms together give me the 2. And P dot A turns out to be 0.
Okay, man. I just got little bit. Seeing the notation. I didn't observe the dot where it is. So
Yeah. So it's dot is in the same place basically.
yeah.
So it's the
Thank you.
same. Okay. So now we have solved the non-trivial sort of term, which is the pi square term. Everything else is multiplicative. And this is also something we have done for one electron. When I write this is only one electron. So if I have a true molecular system, I can just summarize the molecular Hamiltonian now. Molecular Hamiltonian in a magnetic field. That is, so the p square term. So so small I runs over all the electrons in the system. So 1I, 2 number of electrons in the system. So we had pi square by 2m, remember? So 1 by 2m pi square. So the canonical momentum of every electron, and you sum it up. Okay. Then you have so there is 2e. So this is again for every electron. So sum I, then 2e by 2m a dot p. Okay. Sorry, ai pi. Then, so I'm writing I because the AI depends on the position of electron I. So the electron will interact with the vector potential at its own position. So that is why I have the I on the vector potential as well. Then I have the scalar potential is also there, which is basically minus E sum over I phi I. And this one is E square by 2m sum over I ai square. So this is the interaction with the fields, electric and magnetic fields. But I have said molecular, so you all also have the nuclei. So the nuclei interaction is E square by 4 pi epsilon 0 sum over. So K is the index for the nuclei in the molecule. I is the index for the electrons. And the Coulomb interaction of every electron with every nucleus needs to be counted. And Rik is the distance between electron I and nucleus K. Then you have E square by 4 pi epsilon 0 sum over. So when I write I not equal J, I will go over the unique pairs of electrons. So I and J are the indices of the electrons. We have 1 by Rij. So what is the 1 by Rij? This is the Coulomb repulsion of the electrons among each other. Okay. So now we've covered all the interactions in the molecular Hamiltonian in a magnetic field, and also if if I've written the scalar potential, I might as well write electric field as well. But static.
as well.
Yeah. But static, okay? So if it is not a static one, then everything becomes far more complicated. Okay, so now I have all the interactions here. And I can say something more here as well. So in the absence of the field, this is the Hamiltonian. So we can call this, let's say, the zero order Hamiltonian. Zero order. Okay. Then in this one, this part, I have the vector and scalar potential at linear order. So I can call this first order part of the Hamiltonian. And this has a second power. So this is the second order part of the Hamiltonian when we're considering the interaction with the fields. Okay. So one thing I have ignored over here is spin. So I will talk about this in some subsequent lecture if we have time, and we will introduce spin into the picture as well. But for now, it's enough to do just the orbital effects.
Ma'am, just a small thing
Yeah.
means in the zero order in Coulomb interaction, sigma I.
Zero order Coulomb interaction, sigma h. I didn't follow, sorry. Can you just repeat once more?
I'm telling there is double summation, right? In
Oh,
Coulomb
yeah, in
interaction.
the last one, yes. Yeah. There's sum over I and sum over j.
Yeah.
Yes. That is right. So, and if I did not want to take unique pairs, I could put a half and unrestricted sum on I and j. I can also do that. Okay, so I wanted to actually teach a lot more. No, maybe, okay, we didn't get to the London orbitals. Do you all have some more time today? Can I continue or?
Actually, sorry, ma'am. Actually, but next day we can do more.
Okay. Then I'll do it next day because it's a little bit too much also to do continuously. But we didn't reach the London orbitals.
Yeah, yes, I am.
But okay, so Friday only, or should I take another one on Thursday?
Oh, you can take, no problem. Ma'am, I just request if you, in this week, instead of time from 3:30, if you can take from 2 to 3:30, it will be good.
2 to 3:30. Actually,
Ma'am,
2 becomes a bit difficult for me. Maybe 2:30.
ma'am, this Friday you told 2:30 only, right?
Yeah. So one day Nikhil had a problem. I said 18th or something. I
Yes,
said
ma'am. This Friday would be the 18th.
okay. Yeah. Then it's anyhow 2:30. Yeah, no problem.
Yeah, actually, this week from 16 to 28th, I have some other things. So from 4 to 8, I will be busy there. That means want to ensure it will be. If you shift from 2, then even if you continue for 1.5 hour, I will not have any problem.
Okay. So okay, if I'll let you know. I'll try by 2 o'clock. Actually, I have to. So my son finishes lunch, and then I eat lunch, and then I can teach again. So that is the.
Okay.
So it
Uh,
sometimes takes more time. But okay, I'll
uh,
try it from 2 o'clock. Yeah.
yeah. Okay. Please. Thank you, ma'am.
Okay. Yeah. Okay. Wait.
Thank you, ma'am.
Yeah. That's so I will just end the
And
call then. Yeah. Just 1 minute.
this. Hello.
Yeah, I'm just trying to end the call.
Yeah. Okay, ma'am.
Yeah.
Yeah.
Okay.
Actually, I just got yesterday. I just want to clarify one thing. Yesterday, I got one mail telling a interview with director. So, is it for PMRF or
Yeah. Yeah.
because
Tell me.
in on the 18th they told I just received a mail from
Oh, this
Rahul Gandhi.
interview, this Inspire interview.
Inspire interview. Okay, okay.
So 18th, so there is this policy for the inspired PhD fellows that they have some interaction with the director and other faculty before final selection. So it's some sort of additional screening in a way.
Oh, okay, okay, okay. Just
So
got
that is what you have.
yeah. Because I didn't understand because in the mail they didn't mention anything. Just told interview. So, okay, thank you, ma'am.
Yeah, it's for the PhD recruitment only. So they have this additional step for inspired students.
Okay, okay, ma'am. Thank you.
Okay.
Thank you, ma'am. You
Yeah,
can
yeah,
end.
fine. Yeah, I will also be there on the
Yeah, yeah, okay.
yeah. Okay, bye bye, Nikhil. Bye bye, Stephen.
Take care, ma'am.